Hello, class. Sorry this lecture is coming a little late, but we're just gonna get started. So today we've left the book, and we're hopefully going to do some stuff that's going to be different and interesting. So today is lecture number 18, and we're going to talk about Intro to Quantum Information, what that is, Bell's theorem, quantum cryptography, and maybe, talk a little bit about the no cloning theorem. So this is sort of my field of expertise, and there's a big sort of industry now. Both large corporations and smaller startups all over the world are all working on new techniques and devices in quantum information, right? Of course, you have probably heard of quantum computers, which would be the most notable product of this field of inquiry. There are a few that exist, but at the level of 30 to 40 bits that run on the computer. I think the one at Google has 50 or so. And that's the record. So not really any practical devices yet, but things get better and better. And there's a lot of promise that comes with these new types of quantum technology, which is why, even though it's so difficult and so expensive, and physicists have been working on this for decades, people are still working on it, right? So today we're going to learn about how all that works. Well, not all of it, but some of it. And yeah, hopefully that'll be interesting. So we've seen that quantum mechanics gives us a good and accurate description of the world. Hold on, I'm getting my glasses. Can't really see my camera very well without my glasses. Okay, all right, that's better. So we've seen that quantum mechanics gives us a good and accurate description of the world. It is extremely predictive, and from the perspective of how accurate it is, right? It's one of the most successful theories in physics, right? People have been trying to disprove quantum mechanics or find things that are wrong with it a lot because it's so counterintuitive. People think that this on first encountering it, this stuff shouldn't be true. This must be an approximation or something like that. So people have tested quantum mechanics over and over and over again, and always it seems that the predictions of quantum mechanics are what are maintained, right? So the problem with quantum mechanics is that there are a number of implications that seem impossible, or from the perspective of common sense would seem to violate, right, that common sense. So quantum mechanics is full of a lot of counterintuitive notions and things that are just generally weird, right? So what I'd like you to do is pause after I give you some instructions, and then make yourself a list. I would like you to make a list of all the things that you think are weird about quantum physics, right? So, just to start you off, one thing might be the Heisenberg uncertainty principle, and that you can't completely define an object's momentum and position simultaneously. Right, so go make that list, pause, resume. Okay, so I'm going to give you my list. If we were in class, this would be much smoother, right? You would call things out and I would write them on the board. But, okay. So, quantum weirdness. Maybe this thing needs to be turned this way a little bit. No, that looks worse. No. I feel like every time I do this, it's different. It doesn't work as well. Maybe. I guess that's good enough. I mean, it looks kind of cockeyed. Now, for this one, maybe that's better. Okay. It just feels weird to write. I'm writing at an angle, kind of. Anyway. No, this is uncomfortable. I can't write like that. You'll just have to deal with it. It's a little slanted. Okay. Sorry about the interruption while I adjusted things. Okay, quantum weirdness. And all of my markers are dying. All right, can I use green? Will green show up okay? Okay. Well, okay. Quantum weirdness. Restriction to discrete variables. So this would be, in a word, quantization. So for the best example of this, think of your Stern-Gerlach experiment, right, where we bent some spins, right, some spins from an atom, right, the electron in an atom, either up or down when it went to a magnetic field, right? And we only saw those spins hit the photographic plate in one position at the top or another position at the bottom, nothing in between, right? Which means that when we measure the spin of those electrons, we get either an up result or a down result. We don't get anything in between, we just get one of two results. Okay, so this is one of the first things that's weird about quantum mechanics is quantization. Can you see when I write in green? Kind of. It's difficult to tell because everything looks backwards to me when I look at the camera. So, difficult to tell if what I'm writing is legible or not. Okay, hopefully this is all legible, and if not, hopefully I'm speaking clearly enough. Okay, another weird thing is that values not defined prior to measurement. Okay. And we could call this the observer effect. Or measurement probability. So if we have a quantum wave function that's spread out, right, somewhere in space, you can think of whatever kind of wave function we've studied up until now in this class, right? If we measure the position of something given by a wave function, we don't know in advance what values that thing's going to take, right? Quantum mechanics doesn't give us a mechanistic theory that tells us, okay, this thing hits that thing, it goes over here, this blah, 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 like you would from mechanics, right? It's not like a clock that runs. The only thing we get in terms of our prediction is the probability that the measurement will turn out a certain way. So if we're looking at the position of a particle, maybe it has some Gaussian wave function, right? It's most likely to be where the peak of the Gaussian is, but it could be anywhere. So if I ask the question, when I measure that particle, is it going to be on the left of the peak or the right of the peak? Essentially, that answer doesn't exist until I measure that system, right? Until I find the position of that particle. Okay. Another weird thing is that physical objects I'm a physicist. You would think I would be able to spell the word physical, but here we are. That physical objects can exist simultaneously in mutually contradictory states. And we could call this superposition. Okay. So, when I'm talking about this, for example, when I'm talking about the spin of a particle or the polarization of a photon, which is like the spin of the photon, when I do that measurement, right, I just get up, down, vertical polarization, horizontal polarization. The particle is on the left-hand side, the particle is on the right-hand side. But before I do that measurement, that particle is simultaneously in all the states that its probability distribution will allow, right? So if I have a particle going up or down in my Stern-Gerlach, well, before we make that measurement, right, the particle is going both paths in the Stern-Garter lock, and only when it interacts with the photographic plate that measures its location, only then does that wave function collapse to one state or the other. Before then, the particle is moving up and moving down simultaneously, right? So that's one of the very strange things about quantum physics, is that things can be in multiple places at the same time, and it's not just that we don't know where the object is, it's that the object doesn't have a defined location, right? I got two more, which hopefully fits on the board and on the screen. Maybe if I tilt. No, I'm not going to mess with that anymore. Okay. Another weird thing is some properties cannot be simultaneously defined. Sorry, my handwriting is getting worse and worse. And we could call this complementarity. Or the Heisenberg uncertainty principle. Okay. Remember, our Heisenberg uncertainty principle tells us that if we look at the position and momentum of a particle, right, if we accurately define, i.e. measure, the position of a particle, its momentum becomes very highly unknown. Same with the other way around. If I very highly determine the momentum of a particle, well then I don't know what its position was, right? So the best way to see this is to think of momentum and position in terms of Fourier transform pairs, right? Things that are very restricted in time space are very, things that are restricted in momentum space are very undefined in position space, and vice versa, right? If I have one plane wave that's got a very highly defined momentum, but it's anywhere in space because that plane wave goes from positive infinity to negative infinity, right? And likewise, if I have something that's very well defined in position, when I take the Fourier transform of that, I get something that's very broad. Okay, so we have, since everything is made of waves, and waves have this Fourier relationship between time and frequency and between momentum and position, right? If we define one thing, the other thing becomes undefined. And that's not just for momentum, position, time, frequency. There's a lot of complementary variables in quantum physics. Those are just the easiest to understand. Okay? And the last weird thing I found on my list is that particles can travel to quote-unquote forbidden places. Okay. All right, what do I mean by that kind of cryptic statement, right? Quantum particles can break quarantine, right? If they're trapped in some potential well, if that potential well isn't completely infinite and going on forever on one side, well then part of that quantum particle's wave function can extend beyond the potential barrier onto the other side, and that's what allows the effect of quantum tunneling, right? That particle can cease existing inside the potential well and appear outside the potential well. And even though it's called tunneling, it's not like the particle is physically driving or burrowing through some material. It's that it stops existing in one place and starts existing in the other. And this is essentially a direct result of the fact that values are not predetermined prior to measurement, so pieces of wave functions can leak out of potential wells. Okay. All right. So if I just, without any preamble or teaching you anything first, said all of these things are true, I mean, you never heard of anything before, you think I'm a madman, right? This is all sounds fairly insane at the face of it. So how do we know that all this stuff is true? In fact, when Einstein laid most of the groundwork of the old quantum theory, and people built the new quantum theory on top of it. Einstein never thought that quantum mechanics was in itself complete. What he thought was that quantum mechanics was just an approximation of a deeper, unknown, fundamental theory, and that this theory, once known, would do away with all of these weird contradictions that didn't seem to make sense or flew in the face of common sense, right? So he thought that once this new theory was known, we would, of course, see quantum mechanics as just being an approximation. And that's why it gives us probabilities, because it's not the full mechanistic theory yet. So this is something that Einstein called potentially some hidden variable model. Actually, I don't know that Einstein would have called it a hidden variable model, but it's what we call it now. I guess I should look up who coined the term hidden variable model. Maybe John Bell, who we'll talk about in a little bit. So hidden variable model just means that there is some model that gives us mechanistic predictions about how the world behaves and does away with all this weird stuff. But these variables that determine how this model behaves are hidden from us, right? The variable about the particle's position is unknown to us, but it exists in this deeper model, in this deeper theory, right? In that deeper theory, all of the positions and momenta of all particles are tracked all the time, and this apparent randomness is just because we don't see how those deeper hidden variables relate to the things that we can measure, right? And so as we start talking about hidden variables and hidden variable models, it's important to point out that we never assume that the hidden variable model has any specific properties other than very general ones, right? We don't say, okay, this specific hidden variable model makes these predictions. We say things like any potential hidden I had to emphasize the right word. Any potential hidden variable model with some very broad class of characteristics, right? Those are the models we'll talk about, not any kind of specific thing. So he felt that quantum mechanics was incomplete, and once we knew this deeper theory, this hidden variable model, then we would understand the world. Okay. So how can you test between these two situations, right? Or two possibilities. Now, quantum mechanics is simply correct, and with all the weird things that implies, or that there is some hidden variable model that mechanistically predicts how the world behaves, like classical mechanics, right? So before we talk about the hidden variable model and how to prove or disprove its existence, we're going to talk about something called entanglement. So entanglement is a kind of superposition shared by two or more particles. Okay. So a kind of superposition shared by two or more particles, and what this means is that if I have some particle A, and that can be over here or over here, and some particle B, and that can be over here or over here, an entangled state of these two particles would look like psi total equals psi A x1 psi B x2 plus psi A x2 psi B x1. Okay? So this wave function tells me that if particle A is in position x1, then particle B must be in position x2, and if particle A is in position x2, then particle B must be in position x1, and both of those mutually contradictory things simultaneously. And what that means is if I perform a measurement over here on A, and I get the result, it's an x1, then it must be the case that B is in x2, right? And vice versa. If I measure x1 over here, then it must be the case that B is in position x2, right? But both of those things exist as possibilities in a mutually contradictory sort of dissonance until we make this measurement, right? So this means that in some sense, if I collapse the wave function over here just by measuring it, then no matter what else is happening over here, somehow there's some influence or something that causes that wave function to also collapse over here, okay? Which is strange, right? Okay. So how could we make such a situation? Well, we can actually go back to something when we were talking about nuclear physics. Remember that when we were talking about the strong nuclear force, that this strong nuclear force only directly bound quarks together via gluons, and that the binding that took place between the individual nucleons, right, made up of quarks inside a nucleus, the neutrons and protons, the thing that bound those to each other inside the nucleus, was sort of a residual nuclear force that was made up of basically electron-positron pairs being passed back and forth between those two parts, or two nucleons, right? And I drew that really large diagram, and I said, okay, this interchange that takes place in the center, that's a constituent particle called a neutral pion, okay? Yeah, I mean, it also is an elementary particle. Cat's being feisty. But it's made up, in a sense, of a electron and positron. It can decay into an electron or positron, right? That's how its Feynman diagram looks like if we go back to Feynman diagrams. So I have a neutral pion, right? And of course, a neutral pion has no charge. It's neutral. Right? And it also has no spin, but it decays into particles, an electron and positron, that together have no spin and together have no charge. But when they separate out, one's going to have one unit of spin and one charge, and the other's going to have the other unit of spin and the other charge, right? Together they add up to 0 and 0, but apart they have some spin and charge. So I have, let's say, an electron and positron here, and a electron and positron here. Okay? So this decay can happen, and I can have a positron shooting off this way, an electron shooting off this way, or an electron shooting off this way, and a positron shooting off that way. And no matter what direction they're spinning in, their opposite has to be spinning, right, in the opposite direction. Okay. But these things are not defined until we measure them. So until I make this measurement, this neutral pion has decayed into both a positron going to the left and an electron going to the right, and simultaneously an electron going to the left and a positron going to the right. Okay? And then these spin states, right, give us another continuous variable that's tuned between them, but those can also be the opposite of each other, right? Just like this. So the spins can be, like, one thing I want to quantify, the spins can be found in any direction, right? But when I make that measurement, it's either aligned or anti-aligned for that measuring device. But I can rotate my measuring device in any direction, right? So the spin's coming at me, it's in all possible states at once perhaps, and then, but I'm still free to choose a direction in my measuring device. So what I choose for this, when I make that measurement, I get a spin aligned with it and a spin anti-aligned with it, right? But I'm still free to choose that direction. Okay. So the spins are always opposite, but I can choose opposite with defined with respect to what, essentially. Okay. So this entanglement and this neutral pion in more modern versions of this is really just a thought experiment. the way that people actually do this is typically with the polarization of the photon, and we'll talk about that either this class or the next class. Okay. So what this does is give us, in principle, a way to test the observer effect and detect the presence of a hidden variable model. So we're going to follow some of the same logic that was come up with in 1964 by John Bell, who decades after the advent of quantum mechanics was the first to find a way to distinguish between the idea that the quantum mechanics we have is complete in a sense and gives us all the correct predictions and there's not a deeper level beneath that, or the idea that quantum mechanics is approximate and there is a deeper theory, a hidden variable model beneath that. Okay. So we're going to follow a reformulation or simplification of Bell's theorem that was done by Eugene Wigner. So Wigner, you'll see his name everywhere. He did lots of stuff in physics. Okay. So let's write down some assumptions. So what we're going to do to show that quantum mechanics is not representative of a deeper hidden variable model so far as we know, is construct a proof by contradiction. So we're going to make some assumptions, right, that are going to be the opposite of the assumptions we want to prove. And what we're going to show is that a model, a general mathematical model based on those assumptions can't work in reality. So it proves that the conjunction of those assumptions, right, those three assumptions taken together, is impossible. It's logically impossible. Okay, so what are those assumptions? Basically, we're building a straw man and then taking him down. So the assumptions are anti-correlation, which is just that the spins are always opposite. Hey, stop that. He's messing with my shit. Right, if I measure one of those particles as spin down on the other side, if my measuring devices are aligned, it's going to be spin up on the other side. The other is definiteness or realism. Right, which is essentially saying there exists a hidden variable model. Right, if you haven't seen this weird backwards capital E, it means there exists. So this is the part that's in contradiction to quantum mechanics. That values don't come into being when we make the measurement. Right? They exist before we make the measurement, and us making the measurement just reveals these values, right? It's not the case that the particles spin up and spin down simultaneously. It's one or the other. It's just really difficult to tell, and then when we make our measurement, that's when we find out. Okay. So this is, realism. The world really exists definitely apart from our interaction with it and measurement of it, right? Definiteness is that, physical values are definite, right? They're not given by probability distributions. They have a single value. It's just that we don't know. And the third assumption is locality, which is that space-like separated events do not influence each other. So this is a bit of relativity, right? It's just saying that if we, create those two spins that we know are opposite, but the values are undefined, if we create them at one point and we let one fly to one part of the universe and the other fly to the other part of the universe, when we make a measurement on the one over here, any kind of information that would travel between those two separated events is limited to the speed of light, right? That I make some measurement over here, and not instantaneously does some information reach the other side of the universe. Now, that might seem to be in contradiction with the idea of entanglement, because you might think, well, how does the other particle know on the other side of the universe to change if it can't get any information? Well, that's kind of a sticky subtlety, right? We're not saying that those correlations can't appear after measurement, right? We're saying that information itself can't travel faster than the speed of light. Okay, so you know, if you're fans of science fiction, you'll oftentimes see in science fiction, you know, some kind of quantum communication device that can send signals faster than the speed of light. You can't use entanglement to send signals faster than the speed of light, because though you can be assured that the two results of those measurements are correlated, right? If I get spin up over here, then instantly this one's going to be spin down over here. I can't make this one be spin up or spin down. I get a random result over here, and then the opposite random result over here. So even if you and your friend on the other side of the universe are measuring spins like crazy, you can't make that transmit any information because you're both getting random noise. It's just that you're getting correlated random noise. So you can't use entanglement to send messages. So this is, quantum mechanics obeys locality because I cannot use that non-local influence to send any kind of information. Okay, so though